Hello, Calculates. We're going to talk about limits and their properties, starting with Chapter 1 today. So, Section 1.2 is the first section we're going to start in. And then our objectives for today are to estimate a limit using a numerical or graphical approach, and then learn different ways that a limit can fail to exist. So let's focus on this graph for a minute. Suppose you're asked to sketch the graph for the function f, which is x cubed minus 1 over x minus 1. Obviously x cannot equal 1, because if you put a 1 in, the denominator would equal 0, and you can't have a denominator equal to 0. So this graph looks like it's a parabola, but actually it has a hole at the point 1, 3. So that's the graphical, that's the graph of x cubed minus 1 over x minus 1. Let's look at it numerically. To get an idea of the behavior of a graph near x equals 1, you can use two sets of x values. One set that approaches 1 from the left of 1 on the x-axis, and one set of x values that approaches 1 from the right of the x value of 1 on the x-axis. So, for example, if we take a number like 0.75, that is to the left of 1, and we plug it into the function of x cubed minus 1 over x minus 1, you get 2.313. And as we get closer to 1, like we choose 0.9, that's getting closer to 1, and plug that in, the y value gets a little bit higher. If we plug 0.99 into x cubed minus 1 over x minus 1, we get 2.970. So as the x values get closer to 1, what does it look like the y values are approaching? Obviously, the y values approach 3. That corresponds with what we just saw on the graph. As x gets closer and closer to 1, the y values get closer and closer to 3. And what about from the right? If we choose a number like 1.25, 1.1, 1.01, those x values are getting closer and closer to 1, and the y values are decreasing and getting closer and closer to 3. So since from the left and the right it appears that the y values are approaching 3, since they're approaching the same number, we can say that the limit of this graph as x approaches 1 is 3. And here's how you write that. Wait a second. Limit as x approaches 1 of the function is 3. So this is the x value, and this is the y value that the graph approaches, but that value may not actually be a point on the graph. All right? So the graph of f is a parabola that has a gap, or we call it a hole, at the point 1, 3. Although x cannot equal 1, you can move arbitrarily close to 1. Arbitrarily means there's no certain distance that you're going to go away from 1. You're just getting closer and closer. As a result, the f of x moves arbitrarily close to 3. So this is called limit notation, and you read it, the limit of f of x as x approaches 1 is 3. So instead of writing all those words in math, we just write this shortcut, okay? This discussion leads to our informal definition of limit. If f of x, that's the y value, becomes arbitrarily close to a single number, we'll call it L, it was 3 in the previous example, as x approaches c, so that's a specific number, and in our previous example it was 1, from either side. When they say either side, they mean both sides. It has to be both sides. They use the word either to mean both. It's not like one side or the other. So it has to approach the same, the y value has to approach the same y value from the left and the right of the letter c. Then the limit of f of x as x approaches c is L. So that's the formal definition, or kind of an informal definition. So to estimate a limit numerically, so we just did a numerical limit by looking at a table. Evaluate the function f of x equals x over the square root of x plus 1 minus 1. at several points near x equals 0, and use the result to estimate the limit as x approaches 0, which is x over the square root of x plus 1 minus 1. So in the table of values, we want to approach an x value of 0, and these are our x values, and these are our y values, and we want to approach 0 from the right and the left. So numbers from the left would be like negative 0.5 and negative 0.1 and negative 0.001, and then from the right, values like positive 0.5, positive 0.1, positive 0.001. And we're going to plug those into this equation and find what the y values are equal to. Now, if you're using your graphing calculator, the easiest way to do this is go to your y1 and type in the function, which if you can see up here, I've got a good example of where to put parentheses. So x divided by parentheses. That got messy quickly. The square root. And then your calculator puts in a parenthesis here, x plus 1, so make sure you close that parenthesis to show you're done with the square root, minus 1, and then close the parenthesis to show you're done with the denominator. Put that in y1, and then you can either go to table. If you go to table, you're going to have to change what the table counts by to get these values. Or if you'd like to, you can go to second window, which is table set, and have it do it for independent. Go to ask for the independent variable. And then when you go to table, it will give you a blank table of x and y values, and then you can type in like negative 0.5, and it gives you the y value of 1.7071. And then type in negative 0.1, and it gives you 1.98487. And then you can type in negative 0.001, and it gives you 1.9995. So you can see that these may be approaching 2. Let's try this. It's 0.5 gives you 2.2247. Oops. And then 0.1, 2.04. This table feature is really nice. You don't have to keep typing in the whole thing, the whole equation. Just type in the new number that you want, and it gives you the y value. Please ask me in class if you don't know what I'm talking about. So you can see as x approaches 0 from the right and from the left, it appears that the y values are both approaching 2. So again, you go to table set, and where it says independent, instead of auto, you change it to ask. And then you go to table, and then type in the number in the x column. So there's our table. You can see that both values approach 2 from the right and left. So then we say the limit as x approaches 0 of the function, or if you want to actually write in the function there you can, is 2. If you look at the graph of this, you can see that the graph verifies what we're talking about. The x values approaching 0 from the left produce y values that approach 2. And the x values that approach 1 from the right, or 0 from the right of 0, the y values approach 2. There's a hole there at 0, 2. It's undefined. The graph has no point there, but the y values approach that, so it does have a limit. There are some limits that fail to exist. For example, if we have this graph, it's a step function, the absolute value of x over x. These limits would exist if I asked you for the limit as x approaches negative 1 from the right and the left. The y values both approach negative 1. And that's an actual point on the graph. That limit exists. But if I ask you for the limit as x approaches 0, from the right the y values approach 1, and from the left the y values approach negative 1. Since they both approach 2 different values, then that graph does not have a limit. So if the behavior differs from the right and from the left, the graph does not have a limit at that point. So that's one that fails to exist. Other things that fail to exist. So this is the one we just talked about. F of x approaches a different number, so the y value is a different number from the right side of C and from the left side of C. Another way that a limit fails to exist is if the y value increases or decreases without bound as x approaches C. So that looks like this. Let's say here's our value of C. If the graph from the right goes up and the graph from the left goes up without bound, means it goes on forever, then this limit does not exist. And you can abbreviate that by saying DNE. The limit does not exist. Even if the graph, the left side goes up and the right side goes down at that point where you're trying to find the limit does not exist. Or if the function oscillates. Now I know you've heard about an oscillating fan, which goes back and forth and back and forth. Well, a function that oscillates, say we're going to talk about the function right there at C, a function that oscillates goes back and forth and back and forth, back and forth and back and forth between two y values before it continues on. So at that point, the graph does not have a limit. So there are 3 ways that a limit fails to exist. So here's an example of a graph that does not have a limit. So the limit as x approaches 0 of 3 over x equals, and then we just write does not exist. If we asked you for the limit of 3 over x as x approaches 3, that limit does exist because from the left and the right of 3, the y values both approach 1. That limit is 1. That's actually a point on the graph. That's fine. It could be a hole or a point and the limit would still exist. Oscillating behavior, the limit of sine of 1 over x as x approaches 0 does not exist because the graph just goes crazy up and down in between 0 or negative 1 and 1, so there's no limit. This is how I remember it. Oh, I typed that wrong. This is how I think about limits that don't exist. Here's how I think about limits that don't exist. There is an Applebee's in Maple Grove, right? And there's an Applebee's in Rogers. If I told Ms. Sievoldson, hey, let's meet at Applebee's, and she went to the Applebee's in Maple Grove, and I went to the Applebee's in Rogers, we're both going to 2 different places. This limit does not exist because the 2 different destinations were different. Okay? There used to be a Chi-Chi's in Coon Rapids. And if I told Mrs. Froming, let's go to Chi-Chi's in Coon Rapids, because I learned my lesson here, you got to say where. So I drive there, and it's just an empty parking lot. And Mrs. Froming drives there, and it's an empty parking lot. Our actual destination that we wanted isn't there, but we're at the same place. So the limit exists. This is an example of a graph that would have a hole. So we didn't actually get to be at that point that we wanted to be at, but we both were approaching the same point. So a graph with a hole, the limit exists. This would be a graph with a jump, where the graphs approach 2 different numbers, a big jump in the graph. So let's label this jump and label this hole. So if a graph has a hole, the limit exists. If a graph has a jump, the limit does not exist at the point where there's a jump. Okay, let's say I told Ms. Lynn, let's meet at Buffalo Wild Wings in Champlin. It's there, we both go to it, and it's a point on the graph. We get there. Does that limit exist or not? This is an actual point on the graph. Does that limit exist? Yes, it does. This is an example of Mrs. Lammers going up to Canada and Ms. Veertz going up to her house in St. Cloud. We're both heading in the same direction, but we're just driving on forever and never meeting up with each other. That limit does not exist. That's an example of a graph that has like an asymptote, a vertical asymptote. And then, oh, you can't see this very well. Let me move it up. Ms. Harapat and I like to go to Lifetime, and we both get there, but we're on 2 different elliptical machines, and I'm going up and down real fast, and she's going up and down real fast, and we're just not together on the same thing. So I know it's kind of a stupid example, but that's a graph that oscillates. So does that limit exist? We're saying no. It's not a very good example, but That's what I came up with. So just some strange real-world examples of when a limit exists and when it does not exist. So in the future, when I ask you when a limit exists, make sure you talk about at a hole or an actual point on the graph, or places where a limit does not exist, a jump where the two ends don't match the same point, an asymptote where they go on up forever without bound or down forever without bound, or a graph that oscillates. Okay? Here's your homework, page 54, 1 through 31 odd. Have a great day.